Good afternoon, everyone. Myself, Professor Jalpasha, Assistant Professor in Computer Engineering Department, Aditya Silver Oak Institute of Technology, Silver Oak University. Today, we are going to see the topic of the subject, that is analysis and design of algorithms. In short, it is known as ADA, which comes in the 5th semester of the curriculum. So in today's presentation, we will see the topics, that is analysis of the algorithms, recurrence equation, substitution method. In that, there are two parts of the substitution method, that is forward substitution method and the backward substitution method. Next is the master method, and last one is analyzing control statements. So the learning objectives of today's lecture is to analyze the asymptotic performance of the algorithms, write rigorous correctness proof for algorithms, demonstrate a familiarity with major algorithms and data structures, apply important algorithmic design paradigms and methods of the analysis, synthesize the efficient algorithms in common engineering design situations. So now, starting with what is the efficiency of the algorithm is that it can be specified using the time complexity and space complexity. That means if we need to measure that how our efficient algorithm is, so there are two parameters through which we can measure that efficiency. First one is the time complexity and the second one is the space complexity. So now first we will see that what do you mean by time complexity. Time complexity, that means amount of time taken by an algorithm to run. That means whenever we will run our algorithm, whatever will be the time taken to execute that particular algorithm will be considered as the time complexity. Now the space complexity. Space complexity, that means it means amount of space or the memory taken by an algorithm. That means whenever we will write an algorithm, the amount of space or the memory that will occupy in your system will be considered as the space complexity of that particular algorithm. So now, let's see the importance of that particular efficiency analysis. So by computing the time complexity, we come to know that whether the algorithm is slow or fast. As we have seen that time complexity will be measured by time taken to execute that particular algorithm. So we, according to that time complexity, we can say that our algorithm is slow or fast. Now by computing the space complexity, we can analyze whether an algorithm requires more or less space. That means the amount of space that will be acquired by the algorithm, that can be more or less into your system. So now according to its efficiency, we need to define its complexity. So that we can define with the help of the notations that is known as the asymptotic notations. So to choose the best algorithm, we need to check the efficiency of each algorithm. So asymptotic notation is a shorthand way to represent the time complexity. Using this, we can give the time complexity as the fastest possible, slowest possible, or the average time. So here, asymptotic notations to define that above 3, that is big O, omega, and theta, it is known as. So big O will represent the fastest possible, omega will represent the slowest possible, whereas theta is the average time. Big O is also used to define the upper bound, whereas omega is used to define the lower bound. Now, to solve whatever the recurrence equations are given to us, we can solve or we can find out the time complexity for that particular recurrence equations. So first of all, we will understand that what do you mean by recurrence equation. So it is an equation that defines a sequence recursively. It is normally in the following form. First one is T of n is equals to T of n minus 1 plus n for all n greater than 0. And T of 0 is equals to 0. So here we can say that equation 1 will be known as the recurrence relation and equation 2 that is t of 0 is equals to 0, is known as the initial condition for the equation. So always whenever you need to solve the recurrence equation, you are given two equations. First one is the recurrence relation equation and the second one is the initial condition. So now recurrence equation can be solved by the following methods. So there are two methods to solve the recurrence equation. First one is the substitution method and the second one is the master's method. Again, substitution method has two parts, that is forward substitution method and the backward substitution method. So now we will see one by one all the methods that how we can solve the recurrence equation using the following methods. So first we will start with the forward substitution method. This method makes the use of an initial condition in the initial term and the value for the next term is generated. This process is continued until some formula is guessed. Thus, in this kind of substitution method, we use recurrence equations to generate the few terms. So now, we can say that whenever we are using this forward substitution method, it will use the forward method. That means we will take the values of n by values for n one by one and we will try to guess that what is the formula that is going to be used. Now, we will understand this in detail with the help of the example. So let's take one example and we will try to solve the recurrence equation. So now solve the recurrence equation. But so now solve the recurrence equation, that is t of n is equals to t of n minus 1 plus n with the initial condition, that is t of 0 is equals to 0. So now forward substitution method that we will solve. So first, as I have told you, that we have to start with the value of n is equals to 1. So here I have taken in the equation given, that is t of n is equals to t of n minus 1 plus n. In that, if n is equals to 1, then we will put t of 1 is equals to n minus 1. That means 1 minus 1, that is become 0, plus n is 1. So that is t of 0 is 0 plus 1. So we will get answer as t of 1 is equals to 1. Now by increasing the value of n, we will take n is equals to 2. So now if we take n is equals to 2, that means t of n will become t of 2, n minus 1, that is 2 minus 1, that is t of 1, plus n is 2, so 2. Now we already got the value of t of 1, that is 1. So we will put that is t of 1 is equals to 1. So that will become 1 plus 2 is equals to 3. So that means we will get t of 2 is equals to 3. Now again we will increase the value of n. So that is n equal to 3. So now if we put n equal to 3, then t of 3 will become t of 2 plus 3. Already we got the value of t of 2. So that is 3. So 3 plus 3. So we will get the answer as t of 3 is equals to 6. Now, so by observing the above generated equations, are you able to guess that what will be the formula? No. So here we will get the formula, that is t of n is equals to n into n plus 1 divided by 2. So if we remove the brackets, we will get the answer, that is n square by 2 plus n by 2. So always remember one thing, that whenever we are finding out the complexity, whatever the answer that we are getting, in which the highest polynomial degree of the n will be considered as the complexity of that particular equation. So here we can see that the highest polynomial degree of n is 2. So we can consider that will be n square. So here, if we denote that in the big O notation, then the complexity for the equation will be P of n is equals to big O of n square. So this was the forward substitution method. Now, we will see the backward substitution method. So now, in this method, backward values are substituted recursively in order to derive some formula. So in practical, this approach is method used. Why? That we will see afterwards, or that we will see understand by after seeing the example. So by using this method, we are getting the nearest result. So now the same example that we have used in the forward substitution method, that we will consider in the backward substitution method. So you can easily understand that what is the difference between backward and the forward substitution method. So solve the recurrence equation, that is T of n is equals to T of n minus 1 plus n with the initial condition, that is T of 0 is equals to 0. So now by seeing the solution, we all know that if the n is the last value, then the last to second value will become n minus 1. So as we are seeing the solution of the backward substitution method, we will put n is equals to n minus 1 into the given equation. So T of n is equals to T of n minus 1 plus n is given to us. So we will consider that as equation 1. So now firstly, we will put n is equals to n minus 1 into the original equation. So we will get T of n minus 1 is equals to, instead of n, we will put n minus 1. So that will become T of n minus 1 plus n is n minus 1. So here it is n minus 1. So now that will become T of n minus 2 plus n minus 1, and we will give that equation number 2. Now putting equation number 2 in the equation number 1, that is the original equation, we will get as T of n is equals to, instead of T of n minus 1, we will put its answer, that is T of n minus 2 plus n minus 1, and plus n is already there. So now after putting these values into the original equation, we will get this answer. So we will give this as equation number 3. Now let's assume that we are giving n is equals to n minus 2. So if I put that into the original equation, I will get T of n is minus 2 is equals to T of n minus 2 minus 1 plus n minus 2. So that is T of n minus 3 plus n minus 2. So that we will give as equation number 4. So now putting equation number 4 in the equation number 3, we get T of n is equals to T of n minus 3 plus n minus 2 plus n minus 1 plus n. So if we continue the same process, we can get the generalized equation in terms of k. So that is T of n minus k plus n minus k plus 1 plus n minus k plus 2 plus up to n. So now we have to put k is equals to n in that generalized equation. And if we put that, we will get T of n is equals to T of 0 plus 1 plus 2 plus 3 plus up to n. And we all know that initial condition given to us, that is T of 0 is equals to 0. See, if I put that, so that will become 0 plus 1 plus 2 plus 3 plus up to n. And we all know that that is a series. So obviously it is very much easy for us to guess that it is, if it is 0 plus 1 plus 2 plus 3 plus up to n, then it will be n into n plus 1 divided by 2. Again, if we remove the brackets, we will get answer as n square by 2 plus n by 2. So as I said, that is the highest polynomial degree of n will be considered. So the complexity for the equation is T of n is equals to big of n square. So now here you can observe that it is very much easy for us to guess the formula in the backward substitution method instead of forward substitution method. So that's why we can say that practically this approach is possible, whereas forward substitution method is practically not possible. So now coming on to the master's method. So whenever we are going to solve the recurrence relation using the master's method, your equation will be in this form, that is T of n is equals to AT n by b plus f of n, where n is greater than or equal to d and d is some constant. So then the master theorem can be stated for the efficiency analysis as, so these are the basic formulas that are used to solve the recurrence relation using the master's method. So in the formula, it is given that if f of n is theta of n raised to d, where d is greater than or equal to 0 in the recurrence relation, then t of n is equals to theta of n raised to d if we are getting a is less than b raised to d. T of n is equals to theta of n raised to d log n if a is equals to b, and t of n is equals to theta of n raised to log a base b if a is greater than b raised to d. So now if we need to solve one example using the basic equations, let's take one example, that is t of n is equals to 4t n by 2 plus n. So we have to compare this with the generalized equation, that is at n by b plus f of n. So here we can say that f of n is n. So that will be equivalent to n raised to 1. So we can say that d is equals to 1. And here a is equals to 4 and b is equals to 2. So now putting that values into the equation, we will get the condition that is 4 is greater than 2 raised to 1. So that means that will give you the third formula. So we have to put t of n is equals to theta of n raised to log a base b. So that is theta of n raised to log 4 base 2. That is equals to 4 is 2 raised to 2. So if we put 2 ahead, so log 2 base 2 is 1. So that is equivalent to theta of n square. So we can say that the complexity of the given recurrence relation is t of n is equals to theta of n square. Now we have seen the basic formulas. So again, there are three another advanced formulas are given to solve the recurrence equation using the master's method. So here again, that we can say that is the another variation of the master theorem, that is t of n is equals to a t n by b plus f of n if n is greater than or equal to d. So if f of n is b go of log n raised to log a base b minus epsilon, then t of n is equals to theta of n raised to log a base b. If f of n is theta of n raised to log a base b log n raised to k, then t of n is equals to theta of n raised to log a base b log n raised to k plus 1. And the last one is if f of n is omega of n raised to log a base b plus epsilon, then t of n is equals to theta of f of n. Now let's solve one example regarding these variations. So if I take the example that is t of n is equals to 8tn by 2 plus n square, then the solution if we need to find out, then here f of n is n square. So we can say that a is equals to 8 and b is equals to 2. So that is log 8 base 2 is equals to 3. So according to the case 1 of the advanced master theorem, we have to put down, because we are getting n cube and we are given f of n is n square. So to get the n square from 3, we need to minus some constant value. So we have to use the case 1. So that is b go of n raised to log a base b minus epsilon. Now by putting the values, we are getting b go of n raised to log 8 base 2 minus epsilon. So that is b go of n cube minus epsilon. So here we are considering epsilon is 1 to get the n square. So that is our f of n. So t of n is equals to theta of n raised to log a base b. So that is theta of n raised to log 8 base 2. That is theta of n cube. So that is the complexity of the given recurrence equation using advanced master theorem. Now the next topic is analyzing control statements. That means whatever the code is given to us, if we need to analyze that given fragment of code using various programming constructs appear. So those we can consider is one by one. There are 4 types that we can consider to solve this. That is, first is sequencing, for loops, recursive calls, while and repeat loops. So we will see all these 4 into the detail. So starting with sequencing. Sequencing means putting one instruction after another. So for example, if I take the code of 3 lines, so first one is the I is equals to 10. Second is printf %d, I is equals to 10 plus 5. So we have to find out. So we can say that every time each instructions execute only once, because we all know that first line will assign the value 10 to the I variable only one time. Then this statement, that is printf percentage d comma I, will execute only once. It will print the value of I. And then lastly, I is equals to 10 plus 5 means it will add the values of 10 plus 5 and it will assign to the variable I. So here each statement will execute once only. So if we add all that 3, we will get answer as 3. So the complexity or the statement analyzed, that is T of n is equals to 3. Now the next that we have to see the example of for loops. We all know that for loops are of two types. One is the simple for loop and the another one is the nested for loops. So we will see one by one. So starting with the simple for loops. We have to consider one for loop, and we all know that for loop has three parts. One is the initial condition, second one is the main condition, and the last one is the increment or decrement operator. So let's take one example, that is for I is equals to 1, I is less than or equal to n, I plus plus. So now in bracket printf percentage d comma a of I. So the total frequency count of that particular given example of simple for loop is this, that is 1 plus n plus 1 plus n plus n. So if we solve that, we will get answer as 3n plus 2. And as we said that the highest polynomial of degree of n will be considered. So T of n is equals to big O of n. So now we need to see that how it comes. So I is equals to 1 will execute once only. So the complexity or the frequency count for it will be 1. Now I is less than or equal to n. So the frequency count for it is n plus 1. Why? Because I is less than or equal to 1, it will go into the loop, and one extra time when it becomes false, it will check for the condition, so plus 1. So that's why the frequency count for I is less than or equal to n is n plus 1. Now the next is I plus plus. So it will increment n times whenever condition becomes true. So it is n. And obviously it will go into the loop, so it will execute the statement n times. So now if we add all these values, that is 1, n plus 1 plus n plus n, we will get the answer as 3n plus 2. So here we have seen the simple for loop. Now we will consider the nested for loop. So let's take one example of nested for loop, that is for I is equals to 1, I is less than or equal to n, I plus plus. For j is equals to 1, j is less than or equal to n, j plus plus. In that printf percentage d comma a of I. So the frequency count is 1 plus n plus 1 plus n into 1 plus n plus 1 plus n plus n. So if I solve this, that is 2n plus 2 into 3n plus 2, that is 6n square plus 10n plus 4. And the highest polynomial degree of n is square. So that is big O of n square. So now let's see that how it comes. So I equal to 1 will execute one time, less than or equal to n, as I said, that is n plus 1, I plus plus n, j equal to 1, 1, j is less than or equal to n, n plus 1, j plus plus n, and this will be n. So now if we are using a nested for loop, outer for loop will be added and inner loop will for loop will be individually added and it will be multiplied with the outer for loop. So you can see here this is 1, n plus 1, n multiplied with this 1, n plus 1, n, and this n. And if we solve that, we will get big O of n square. Now the next is recursive calls. We all know that what is recursive? That means it is a recursion, which is a process in which one function calls itself. And as we all know that the best example to solve this recursive calls is, or to give, that is the recursion. So that is algorithm factorial n, whereas problem description, that is compute n, input a non-negative number integer n, output returns factorial value. So now if n is equals to 0, then return 1, else return factorial n minus 1 into n. So if we find out the complexity or the frequency count for the recursive calls, that is f of n is equals to f of n minus 1 into n, where n is greater than 0. So we can write the recurrence equation as t of n is equals to t of n minus 1 plus 1. So here, let's assume t of 0 is equals to 1. So t of n minus 1 will represent the multiplications that are required to compute the factorial n minus 1, whereas 1 that is required to multiply the factorial n minus 1 by n. So now we got the recurrence equation. So now we have to solve that recurrence equation by backward substitution method. So that is t of n is equals to t of n minus 1 plus 1. So if I put n is n minus 1, so that is t of n minus 1 plus 1 plus 1. That is t of n minus 2 plus 2. Now, if I put that n minus 2 into the equation, again I will get that is n minus 3 plus 1 plus 2, that is equals to t of n minus 3 plus 3. Now, if we continue the process, we will get the generalized formula in terms of k, that is t of n minus k plus k. Again, we need to put the k is equals to n, then we will get that is t of n is equals to t of n minus n plus n is equals to t of 0 plus n, that is 1 plus n, where t of 0 is equals to 1. So we will get the complexity as t of n is equals to theta of n. Now the last one is the while or repeat loops. So let's take one example. So the while or repeat loops are treated just like recursive calls. While analyzing them, we need to find out how many times the loop is repeated. So let's take one example, that is max value is a of 0, I is 1, j is n minus 1, while I is less than j. If a of I is greater than max value, then max value is a of I. Return max value. So the basic size is input n and the basic operation is within a while loop for finding larger value. So j is equals to n minus 1. Every equation will take one, or every loop will execute only once. Inner statement will execute only once. So it will start from 1 to n minus 1 and one time it will be executed. So we know that is I equal to 1 to n, 1 is n. So if we put that will be become, because limit is n minus 1, so that will become n minus 1. So we will get t of n is equals to theta of n. So that is the frequency count for the given example of while and repeat loop. So we can see that today we have seen the topics. First one is the analyze or the analysis of the algorithms, that is in terms of the complexities. Then we have seen the recurrence equations. To solve the recurrence equations, we have two methods, that is substitution method. Again, it has two parts, that is forward substitution method and the backward substitution method and the master's method. And lastly, we have seen the analyzing control statements using the frequency count. So thank you, everyone. Hope you get the topics. So thank you again.